Math 1314, Tyler Junior College, 2.1, Basics of Functions and Their Graphs. Graphing functions of x. You knew it was coming. Graphs. A lot of what happens in algebra and trigonometry and calculus, linear algebra, differential equations, and a lot of math classes involve functions and their graphs. So we need to figure out how to take a function and turn it to a graph, but let's stop and think about what I mean by a function and its graph. I'm assuming everybody is familiar with where graphs live. This thing is not a graph. This is where graphs are drawn. This thing is called a coordinate plane, but it's also called a Cartesian plane, named after French mathematician and philosopher René Descartes. He's the one who said, "I think, therefore I am," which reminds me of a horrible math joke. René Descartes walks into a bar. The bartender asks, "Would you like something to drink?" Descartes says, "I think not." Poof, and then he disappears in a puff of smoke. Nerd joke. All right, so how are we going to graph? Well, you know, a lot of people think graphing is difficult. It is not. It can be cumbersome, but not difficult. Because the premise behind graphing is actually pretty straightforward. You're playing connect the dots, but the problem is you have to get the dots to connect. When I was a student, I could graph, my classmates couldn't, and I didn't care why they couldn't graph because I was a student worried about my own grades. But when I got into the teaching profession, oh good Lord, how long has it been? 19, 20, 25 years ago. Wow, I'm old. But when I got into the teaching profession 25 years ago, it was my job and my desire to figure out why people had trouble graphing, amongst other things in math. And so I really broke it down into baby steps, and I think I figured out why people have a disdain for graphing. It's not because they can't plot points or connect them, it's because they can't make random decisions. I'll show you what I mean. There is a technique for how to graph f of x. Now, I will admit that what I'm about to show you is not the most efficient technique, but it is universal and will almost always get the job done with enough time and persistence. That said, the more you know in advance, the less work you have to do to graph things. For example, I already know not only what shape this is going to be, but where it's going to be located by simply what's inside the function. At some point, you'll get to that level as well, but for now, let's pretend that you don't know anything about what the graph of this function is going to look like. But do you? We'll see. Here's how to graph any function. Number one, select values for x. And right out the gate, people are like, well, what number do you want me to pick? I don't know, just pick one. I don't know what number to pick. Just pick a number at random. Okay, how many of them do you want me to pick? I don't know until you have enough. How many is that? So people tend to struggle right out the gate with graphing because they can't make random choices. Well, what we're going to do is we're going to make a table. We're going to start by selecting values for x, write them in the first column. Then we're going to evaluate the function for each input and write them in the second column. Remembering that the output of a function is the y-coordinate, we're generating ordered pairs. Ordered pairs go onto the coordinate plane, and then we sketch the graph. But it goes back to, I don't know what numbers you want me to pick. Well, let's just start with 3. All right, let's put in 3 and see what happens. Now, you can be very meticulous about evaluating the function. F of 3 equals 3 squared plus 1, which is equal to 10. But every time you put an input into a function and get an output, you've created an ordered pair. The ordered pair we just created was 3, 10. The input is the x, the output is the y. So that dot can go over here. Now, I'm also assuming that people are familiar with the coordinate plane. So just a little bit of terminology to remind you. The horizontal line is called the x-axis. The vertical line is called the y-axis. The numbers on the right side of the y-axis are positive, and the numbers on the left side of the on the right side of the x-axis are positive. The numbers on the left side of the x-axis are negative. The numbers on the top half of the y-axis are positive. The numbers on the bottom half of the y-axis are negative. In other words, the x-axis is a number line, and so is the y-axis. The point where they intersect is called the origin, because that's where all points originate from. To locate an ordered pair on a graph, you go over the first coordinate, which in this case is over 1, 2, 3, and then you go up or down the second coordinate, depending if it's positive or negative. By the way, we went to the right because the 3 was positive. Had the 3 been negative, we would have gone to the left. So to the right 3, then up 10. This is much more accurate on graph paper, so I'm just kind of freehanding it. But the point for the ordered pair 3, 10 is over there. Oh, and one more vocabulary concept. These two axes partition the plane into 4 corners. Those corners are called quadrants. The upper right corner is called quadrant 1. And for some reason they use Roman numerals. And then they're numbered going counterclockwise. So the upper left quadrant is called quadrant 2. And continuing counterclockwise, the lower left quadrant is quadrant 3. Roman numeral 3. And then continuing counterclockwise, the lower right quadrant is quadrant 4. In quadrant 1, both coordinates are positive. In quadrant 3, both coordinates are negative, left and down. In quadrant 2, the x is negative, but the y is positive. And in quadrant 4, the x is positive, but the y is negative. But I'm assuming these things are somewhat familiar coming into a college algebra class. All right, so can we connect the dots yet? Well, we have one dot. We can't connect anything. So we need more dots. We need more evidence. I don't know what x to pick. Just pick another one. I don't know what to pick. Just pick something besides 3. Oh. How about 2? If you can make random decisions, and these aren't that random, you can probably figure out what I'm going to pick next. Let's substitute 2 into the function, and let's just do this one verbally. If I put a 2 here and square it, 2 squared is 4, 4 plus 1 is 5. Which means my next ordered pair is 2, 5. Let's go ahead and find it. Over 2, up 1, 2, 3, 4, 5. It's a line! No, stop that. Most graphs aren't lines, although we'll be graphing a lot of them. But you can always draw a line through any 2 points, so we do not have enough evidence. And that's really what we're doing. We're getting enough evidence to locate the graph. We need more evidence. Let's pick another number. How about 1? You know what? Never mind. Let's go ahead and put it in 1. If we put in the 1, substitute the 1 for the x in the function. 1 squared is 1, plus another 1 is 2. My next ordered pair is 1, 2. So over 1 and up 2 puts us here. And it might look like it's a line, but unless you know it's a line in advance, don't just settle for a weak evidence like this. Let's put in the next value, 0. And by the way, these numbers don't have to be in any particular order. I'm just doing something that's easy to figure out. 3, 2, 1, 0. If we put in 0, 0 squared is 0, plus 1 is 1. Our next ordered pair is 0, 1. When your x-coordinate is 0, that means you do not move left or right from the origin, so just move up 1. And so that point down there is 0, 1. And at this point, I'm starting to question whether or not it's actually a line. Because although I could just say, well, these are a line, it's just not drawn accurately, this one seems a little bit too far to the left to be collinear with the other 3. So we need more evidence. All right, here's what I was about to say a minute ago. If for some reason you can't choose your own inputs, at random, then I recommend the following 7 values. 3, 2, 1, 0, negative 1, negative 2, negative 3. Why those 7 values? For several reasons. Number 1, they're all pretty small, so the numbers shouldn't get too out of control, but that's not a guarantee. They'll usually behave with these numbers. Number 2, there's 7 of them. 7 points will probably be enough to draw a rough sketch of the graph. Number 3, the values dabble between positive, negative, and 0 because some functions behave differently on negative numbers than they do positive numbers. Now, will this default set of x values always expose the graph? No. So sometimes you need to go get more evidence, but it's a good starting point, and in some cases, it's a good ending point. Let's go ahead and just evaluate the function of these last 3 inputs, starting with negative 1. Negative 1 squared is 1, and then add 1 to get 2. Now negative 2. Negative 2 squared is 4, plus 1 is 5. And then negative 3 squared is 9, plus 1 is 10. I got all these answers already. That's okay. Y values can repeat in a function. Negative 1, comma 2, negative 2, comma 5, negative 3, comma 10. So to find negative 1, comma 2, I go to the left one and up 2 and put a dot here. To find negative 2, comma 5, I go left 2 and up 5 and put a dot here. And then to find negative 3, comma 10, I go left 3 up 10 and put a dot right here in the middle of the word quadrant. It's not really in the word quadrant. Do you see the graph? Did you know before I sketched the graph that it was going to be what's called a parabola? Here. Kind of looks like a U shape. It looks fairly linear on its ends because it's so steep you can't tell that it's not a line. If your graph misses your dots, just make your dots bigger. It's a lame way to hit the points, but you know, as long as the points are labeled, we're okay. So the graph of f of x equals x squared plus 1 is this shape called a parabola, P-A-R-A-B-O-L-A. In chapter 3, the first section, we'll talk a lot more about parabolas. But remember what I said, I already knew what the graph was going to look like because I know how to analyze this function. Some of you may have already known that the x squared is what caused the shape, and the plus 1 means the shape is up 1 off the ground. Things like that are more efficient graphing techniques, but they don't always work because there's so many different functions you could have. This always works and is always cumbersome. And again, these 7 ordered pairs happen to expose this graph. I knew they would. But if you're just picking values without knowing in advance anything about the graph, these may or may not be sufficient, and you may have to find some more values.